Hey everyone, this is the second part of video for the 162 Exam 3 Fall 2019, and I will start from question 7. So if you want to watch question 1 to 6, I will try to link that video in my description or a pop-up link. Starting with question 7, here we're asked to find which ratio test will be invalid, inconclusive. So just for review, root test is where you take the limit of the index or n to infinity of the absolute value of the series n plus 1 term over series at the nth term. And if this is less than 1, then the series will be convergent. Right. So now we're looking at the first one here. So just plug in the values, taking the limit here. They're now taking the absolute value of the n plus 1 term on top. It'll be n plus 1 over e to the n plus 1 will be n plus 2 over the original of n over e to the n plus 1 term. Right. So now we can take this and make all the flip the bottom fraction up, so see this fraction line as a division, and then we can rearrange these terms to like terms. So still taking the absolute value of n plus 1 over n here times e to the n plus 2 term, n plus 2, and e to the n plus 1 on top of that. So I just flipped this one to the division. So you're dividing by the reciprocal here. So n will be bottom here, and the n plus 1 will be top here on this fraction. And then we just continue simplifying this. So here we can see that it's e to the n plus 1 over e to the n plus 2. So we can simplify that. That will go to 1, and that will remain as e. As its exponents. When you divide, you technically minus, so it will be left with e in the bottom. And then you can take the limit of this. The limit of this, so at this point, the absolute values is not that important anymore. So we just need to take the limit of this. We can use L'Hopital rule here, since this is infinity up top, this is infinity in the bottom. We can use L'Hopital's rule, take the derivative. So this would be the limit of n still approaching to infinity of taking the derivative on top is 1 over the derivative of n is 1. So then the limit of this is just 1. And then the limit of this whole equation, sorry, that should not be an equal sign here. So the limit of the equation here, or rather series, the ratio test here will be 1 times 1 over e. Since there's no n term here, you don't have to plug in n here. It will just be 1 over e. So we know that e is something like 2.7. So this is definitely less than 1. So we can say that it is conclusive that the series will be convergent. So 1 will be conclusive. Right. So now let's move on to number 2. Still same idea. We're taking the limit of n to infinity of the absolute value of this at n plus 1 term. So it'd be -1 to the n plus 1 of sine 9n plus 9, since it's sine of 9n plus n plus 1 replaces here, so it would be 9n plus 9 over n plus 1 squared, right? This whole thing is divided by the series at the nth term. And it deactivates series every time I do a series. So just the original series here. Right. And then doing the same thing, we try to rearrange this. So see this big division fraction line as a division. So flip this function and times and rearrange all the terms. And in this step, I usually just get rid of the negative ones, since they do not actually affect the value of this limit. And the absolute value, making sure that no matter it's -1 to the a like even term or -1 to a odd term, that it will still be the positive value. So I usually just ignore the -1 from this step on, and then I just take try to rearrange the similar terms together. So it'd be sine of 9n plus 9 over sine of 9n here times, and this should stay on the bottom, times n squared over n plus 1 squared. And so still taking the limit of this. Right, so you can do the same thing. We can take a limit of this and take a limit of this, time multiply those two together. But we can see from sine here, since sine is actually, if we see a sine graph, it's the it has a period of 2 pi, right? It's always between the values of 1 and -1. But no matter how big the x value gets, it will never come to like a it will never approach something. It will always be some value between 1 and -1. So at this point, we can say that the sine, when you take the limit of a sine value, and to infinity, you take a sine value to infinity, then this is actually dne. You cannot find it, right? So that automatically makes this whole ratio test inconclusive, because you cannot take the limit of sine to infinity. So number 2 will be one of the ones that will be inconclusive. And then we'll move on to number 3 here. So for number 3, same thing, set up the limit of n approaching infinity, absolute value of the n plus 1 term, so 13 to the n plus 1 power over 2 to the n plus 1 squared power over the original 13 to the n divided by 2 to the n squared power. Right, so again, try to rearrange these. So then we have 13 to the n plus 1 on top here, divided by 13 to the nth times 2 to the n plus 1 squared. And on top should be 2 to the n squared. So just one quick note, when you're trying to rearrange these fast, you can always look at the top fraction here, the n plus 1 term. So if it's on top of a fraction, on the top fraction, it will always stay on top, as shown here, right? So the 13 to the n plus 1 term, this top of fraction remained the numerator here. And on the bottom, the denominator, it will be still in the denominator at the bottom over on this fraction. And on the bottom, it always gets flipped. So the 13 to the n goes there, and it will go there. So here, we can simplify further. Here we can say that this cancels out since it's m plus 1 minus n, and then it will be 13 on top here. And then we have this thing. So we can just take the limit of this. So let's just get that out by itself. It's not equal. So this thing, we can see this as an exponent divided by another exponent. So when you divide two exponents, it will be on the same base technically. Then it will be 2 to the n squared minus n plus 1 squared here. And we will take this square out. It will be n squared plus 2n plus 1. And simplify further, so n squared and n squared will cancel, and it will be 2 to the negative 2n minus 1 power. So this thing simplifies to that. So then we can have take the limit a step further here, and we will have the limit of n approach infinity of 13 times so this again, negative power goes to the bottom. It equals to 2 to the 2n plus 1 power, but in the bottom. So we can move that here. Right. So now, since we are taking the n to infinity, so when we plug this into here, it will make this part infinitely large, which will make this fraction here infinitely small, which is approaching 0. And then this whole limit will approach 0, which is less than 1, which will make this ratio test conclusive, and it will be convergent. So the only number 2 here is inconclusive, so the correct answer is B. And as we can see here, 7 is B. Next test, it really, when you see this, you see a series bring up to a power of n. First thing you think of is the root test, and that is taking the series to the say the index is n here, then you're taking the nth root of the index. So now, let's see, take the nth root. Oh, sorry, the limit of n approaching infinity of this is the root test. So then you will have the original series here. So the taken to the nth power and the nth root will cancel out. So then this limit will equal to nth, the limit of nth approaching infinity of 1 plus c squared over n. And when a root test is convergent, it should be less than 1, right? So at this point, we can see that we can take the 1 out since it doesn't have an n here. So you can take this out as a plus. It will be 1 plus the limit of this is less than 1. And then you minus 1 on both sides. So you have this limit should be less than 0. But so at this point, you should be able to think of one thing is that c squared here, since c is a value, c squared should be always more than or equal to 0. If you plug in like 100, it should be 10,000. If you plug in like -1, it should be 1. Plug in 0, it should be 0, but it never is a square less than 0. And the n here, you can just multiply both sides by n. Since n is not 0, that is fine. So you should have like c squared is less than 0, and this is never possible. So then we choose E here. No value of C will make this series convergent. And we can see that A is E. All right, move on to number 9 with Taylor series. So this one is asking for a second order Taylor series. So I don't think anyone would remember a Taylor series for a cosine squared function, but if you do, congrats. But if you don't, we can figure it out really easily by taking the derivatives of this function. So first of all, we have the original function and the function, let's say, so this column would be the functions, and this column will be what the function is at 0. That's f. It's really hard to write with a mouse. So the function is cosine squared x. So when you plug 0 into x, you should be cosine 0 is 1, 1 squared is 1. Then we take the derivative. We then so first it's 2 cosines x, and then you chain rule, take the derivative. Then you have derivative of cosine is sine, is negative sine. I'm sorry. So at this point, you can continue to take the derivative of this, which would have product rule, or you can use a identity of that. Let's write it here. Sine 2x is equal to 2 sine x cosine x. So here we can see there's cosine x, there's sine x, there's just negative here, but we can just bring it out in front, and we can say that this actually equals to negative sine 2x, right? So we plug 0 in here, either one is fine. So we have, if we plug 0 into here, it would be cosine of 0 is 1, sine of 0 is 0, so this thing will be 0. And if you plug 0 into this function, it should be the equation, it should be the same as we plug 0 here. Sine of 0 is 0, so this value is 0. And from this point on, when you take the second derivative, it's definitely easier to take the derivative of this rather than taking the derivative of that. And the second derivative would be equal to -2 cosine 2x. So the chain rule, gotta apply the 2, and then plug 0 into this, should be cosine of 0 is 1, and it would be -2. And since we only need the second derivative, that's how far we really need to go. So then now we can see that, write the Taylor series out. So it's the since it's centered at 0, so the f0 functions. So the first term will be 1 minus plus 0 of x minus 0. So that term will go away. Plus -2, looking at this value here, of x minus 0 squared over over 2 factorial, which is 2. So simplified this, we have f of x is approximately 1 minus 2 here cancels out, x squared as the second order polynomial. And we can plug pi over 6 in from here for x. Then we have f of pi over 6 equal to 1 minus pi over 6 squared should be pi squared over 36. And then we can see that it's a here. And yes, 9 is a. So we will move on to 10 here. And for number 10, it's really the remainder theorem for Taylor series. So it's remainder at term n is equal to the derivative, the n plus 1 derivative, evaluate at c. C is a value between a and x here, and then that over n plus 1 factorial times x minus a to the n plus 1 power. So we can see that we have the original function here of 1 over x. So we need to take this, add third derivative, since over n is 2 of second ordered polynomial. So then the n plus 1 will be taking this as a third derivative, and it'll be 3 factorial here. And x is a value, x is 1.1. Since it's we are trying to estimate this, and it's 1 over x, so x equal to 1.1. And a, as shown here, is 1. And we would be taking that to the third power here. So let's just plug that all in. So first take the derivatives. So the original function, a zeroth derivative is this. And then first derivative, this would be -1 over x squared. Chain, you just, yeah, it's chain rule because this is technically x to the -1 power. And then -1 times 1 times -1, so it'd be -1 over x minus 2, x to the second power. Do the same thing. Now two negatives cancel out, and then this would be to the third power here. That should be x to the third power. And at the third derivative, we would have, oh god, the third derivative should be -6 of x to the fourth. And now we can plug all these in to here. So we have the derivative, which is -6 over x, x to the fourth. I'm sorry, it should be c here. So you're evaluating the derivative at c. So just plug c in for x here. That'd be c to the fourth power over n plus 1 would be 3 factorial is 6. 3 times 2 times 1 is 6. Over here, we have 1.1 minus 1. 1.1 being here, and a is equal to 1 of the third power. So this is 0.1. And here we have 6, which can cancel out on top here. So ultimately, this will equal to -1 over c to the fourth power times 0.1 to the third power. And we can just move this on top here. We find our answer to be A. And for number 10, yes, the answer is A. And moving on to 11, finding the radius convergent for this series. So finding radius convergence or the interval of convergence usually involves ratio tests, since we can, when we take the ratio of the n plus 1 term over n, we take the limit of that. We can see that if it converges, it will be less than 1. So we will, this would give you the general trend you follow for radius convergence. So starting with the ratio test, taking the limit of n approaching infinity, and it should be the series of n plus 1. Sorry, but earlier it should be a, should be something like a over n plus 1 over the series at the nth term. So now, so n plus 1, plug n plus 1 in for n, and we should have, and then it will be x minus 2 to the n plus 1 power over n plus 1 plus 1 n plus 2 of 3n plus 1. That will be the n plus 1 term. This is all over the original series of m squared times x minus 2 to the nth over n plus 1 times 3 to the n And this would all, so we'll again, ratio test, rearrange all these. So it'd be the limit of n taken to infinity, the absolute value of, so first term looking at is the n plus 1, and the similar term to that would be the bottom here of n squared times, and then the second term, x minus 2 of n plus 1 power over x minus 2 to the m. And the third term is here, so that's in the bottom, n plus 2 with n plus 1 on top, times finally this and that, be 3 to the m over 3 to the n plus 1. Now let's simplify this. So here is another exponent, so we can say that will go to 1, and this will just leave up 1 power of x minus 2 here. And we leave this alone for now. And same thing here. We will have 3 left in the bottom of this and 1 left in the top. So for these two, we can see that since it's infinity, when you plug infinity in, and it's infinity squared over infinity squared, and this same thing, infinity over infinity, and then we can use L'Hopital's rule here. So we can take the derivative of this function and find the limit of that. So when you take the derivative, here will be 2m plus 1 over 2n. 2 cancels out. Still infinity over infinity, so you can take it again. Limit. So now you see that it's take the infinity, the derivative of this, it will be, sorry, there's it should be 1 over 1, which is 1. So the limit of n approaching n taken to infinity of this here is 1. So same thing here, we can take the derivative, it will be 1 over 1 again, so it's 1, 1 here. So we have x minus 2 here and over 1/3. So all of this, finding what you wanted to converge, it should be less than 1, which is how ratio tests work. So now we have eliminated all the ends. So now the limit is no longer useful to us. So we can just say x minus 2 from here divided by 3 from here is less than 1. And remember, the absolute value still holds. So when we take the absolute value out, should be 1 more than -1. And we can go here times multiply 3 on all sides. It should be like -3 x minus 2 is 3, and then it would be -1 is less than x is less than 5, and we can see the interval is from -1 to 5. So the ratio, the radius of convergence will be 5 minus 1 minus -1 divided by 2, which is 3. Right here. And we go to 11. It is D. And 12 is basically the same thing, except you find the interval rather than the radius. So do a ratio test here once again. So just taking the limit of n to infinity of the series at n plus 1 term. So x to the n plus 1, n plus 4 plus 1 is 5, all over the nth term. Oh, that should be absolute value. And then this, once again, we try to rearrange this. So, I think it's it was question 7, I think, talk about the negative ones with absolute values. So right now, once again, I'm gonna just take them out since they're not gonna matter within the absolute value. And though we will have the first term being here then of x to the n plus 1 over x to the nth times n plus 4 with n plus 4 over n plus 5. So this, we talked about it in 11 with you take the it's infinity over infinity, so you take the derivative using L'Hopital's rule. You should get 1 over 1, so this is 1. And then here, another exponent, so we would just cancel that with the x on top. And then since there's no n left in the function in the equation, we can just take the limit out too. So we have the absolute value of n is less than 1. And then taking the absolute value out, we'll get the interval to be -1 to 1. So now, since we are asked the interval, we need to test the endpoints. So we will plug -1 and 1 in for x in the function here and see if it changes anything. So usually when interval of convergence is asked is usually with a alternating series, since sometimes when it's a -1, then it will not be alternating anymore. As I will show you here, when you plug x equal to -1 in, then you will have the series being the sum of um, -1 to the nth plus plug in -1 for x, -1 to nth again over m plus 4. And we can see here the exponent rule, when you times two exponent with the same base, you would add them. It would be -1 to the 2nth of m plus 4. Now, since this is an even power always, with n being a whole number, this is always an even power, so we will have -1 to the even power is always 1. So this simplifies to this. Of if you plug in -1 for x here, the series simplifies to 1 over m plus 4. And this is divergent rather than convergent because of the p series. When p is more than 1, then it converges. So you can compare this. You can either compare this or do whatever, compare it to 1 over n, which is divergent, and this is always a little bit smaller. Wait, hold up. Yeah, but doesn't matter as the power here matters, as this is a p of 1, so it will diverge. And then so we cannot include -1 in the interval, but when we plug 1 in to here, it will be 1 to the nth of n over plus 4. 1 to the nth is always 1, so it doesn't have an effect. And now this is still a alternating series, so we can apply the alternating series test. It is alternating from one negative, positive. So with the two conditions, one, this is always decreasing, which is true because n is getting bigger, but um, n is in the denominator. So it gets smaller as n gets bigger. And number 2, the limit of this approaches 0, which is true. Limit of because when you take the limit of n approach to infinity here, then it should be just something like this, and it's on the bottom, so this would approach 0. So you have the two conditions being true, then this converges. So 1 is one of the powerful values. So 1 will have a square bracket here, and then this will be just parentheses, so it will be C. And we can see that 12 is C. So if you're watching this and you are taking this exam soon, I hope you have good luck. I would review, just go through some of the notes on Taylor series and how to just make a Taylor series from scratch. And there should be a lesson on how to choose a convergence test. So you should always just use the divergence test to test if the series is divergent at first. If that's inconclusive, you can try to use the ratio test of just as we used in this video a lot. So ratio test, root test is for situations like this, would be really good for root tests. And then sometimes you will find the ratio test is inconclusive, like here, but usually ratio test doesn't really work on P series. So if you have something like n squared, or like n to the 4th, something like that, and you try to do ratio test of n plus 1 to the 4th, that algebra takes forever, and sometimes it doesn't even work. So sometimes you just gotta look for maybe a direct comparison test, trying to compare it to something. Limit integral test is not as useful, but if you think you can take the integral of something, sometimes it's useful. So overall, thanks for watching, and look on my channel for new videos on Calc 2 and Calc 1, 161 and 162. I might do more of like 165 and 166, but we will see. Thank you.